All right, everybody, it is 2 o'clock. Thank you for being here. I think I'm going to go ahead and get started. I hope that you guys are having a good week and a good day so far today. It's definitely feels summer-like again out there. Lots of sunshine, nice and warm. Let's see, we are really counting it down now. You only have, I can count on one hand how many hours of my lectures you have to listen to. That's what we're celebrating in and of itself. We're just about done with the semester. But we do have an important thing to talk about today. Before I get into the math, let me just remind you, I saw several people with their cell phones out taking pictures of this board here. Not a bad idea. It is all in Canvas because I've updated the Canvas webpage to have all of this information about our midterm. So next time we get together, which is 5 days from right now on Tuesday, we will have the entire class period to take this exam. And you can see what it's going to cover. It goes back a ways. It goes all the way back to somewhere around Halloween when we were in chapter 6. And then through most of November, we kind of worked our way through chapters 7 and 8. And now today we're going to kind of finish up 9.5. That's the one little loose end we need to still tie up together. But you'll get plenty of practice with all of this if you just do those sample midterms that are in the Canvas resources folder. So that's one way to make sure you don't miss anything. If you're kind of trying to line it up with the homeworks and the group works, I put the numbers of the homeworks and group works that are relevant right here. You're currently working on number 23. I guess probably people didn't see over there. During the break, if you want to throw any of the problems on the assignment that's due tomorrow night at midnight onto that board, this morning I answered a couple of questions from it, and I'm happy to do that for you guys as well. At least one of these homeworks was actually just a video to watch, I think, take notes on. But anyway, so those are the assignments that are relevant. In terms of the group works, we've done all of them except number 15, which I'm probably going to just send. I have a copy of it here. I'll probably just send it home with you. I doubt I'll have time to do it with you today. But anyway, there's a few group works that would be maybe worth looking back at as you're getting ready for the exam. But the main thing is going to be to try at least one, if not two, of those sample midterms. I would highly recommend doing that. What I've got on the right side over here is absolutely 100% optional. Nothing over here do you have to do, especially if you feel like you're doing solid on everything. But I am going to do a couple of review sessions. One of them on Sunday afternoon at 3 o'clock. I'm going to be right here in this room. I'll make sure the building is wide open. You can come in and park in the first row and everything on a Sunday. Shouldn't be too bad. And then on Monday, I'll do another review at 7 o'clock down in the basement, not too far from where my office is. I can't use this room on Monday night, but we'll try and do a review there as well. There will be a lot of overlap between the two sessions. Probably I'm going to take Sunday's session and do as many problems as I can from the review packet. And then if I don't quite finish everything, I might spill that over and start with that on Monday and then kind of recycle some of the problems again on Monday night. So again, it's totally optional. Actually, for the second midterm, I did have some people come to both reviews. If that's something that would be helpful, if you want to hear it twice, you can, but you really don't have to come to any review if you don't want to. I will record these sessions, and so a few hours after the sessions, you'll probably get an email with a YouTube link if you just want to watch it at home on your own. But I do think for some people, it is better to kind of come in person if you can, just because, you know, you're sort of focused, you're disciplined, you're not going to walk away from the screen by a bunch of distractions that you might have at home. So if it would help you to be in person, I am going to be here in person to do those review sessions. Also, I have a ton of office hours. A lot of this is extra, not my normal hours. Like Sunday afternoon for an hour before the review, I'll be available. Also tomorrow, I'm going to have a couple of 2-hour stints because there is homework due tomorrow night at midnight. So if you want to dot your I's and cross your T's on anything on that assignment, I hope you'll do that. Definitely you want to do that assignment because it will be on our exam on Tuesday. So that material will be there. And then Monday and Tuesday, of course, right before the midterms, I'm going to be around a lot, quite a bit of the time. So Anyway, I try to be available. I hope somebody's mentioned that in the has anybody done the SOQs yet? A couple people. I found out. So I don't get dinged too badly if the SOQs are bad, but I get dinged if nobody does them. And this is what I figured out. So I have had somebody mention to me, "Oh, your students aren't really filling out your SOQs." So I don't even know who's doing it and who isn't, but tomorrow is the last day to turn those in. So I'm going to beg and plead with you, please and thank you, to fill out an SOQ form for my class. I would love to know things I could improve on or things that you like that you hope I'll keep doing. I'll give you just one example. When we came back from COVID, I thought, now everybody's back in person, so I'll stop recording my lectures. And I did that for a while. I stopped recording them. And then I had some students write down in those forms, which, by the way, they are anonymous. You don't have to sign them or anything like that. But somebody wrote in their forms, actually, several people wrote, "Oh, it would have been so nice if, we had those recordings. We could go back and review, and, if we missed class or if we just wanted to review something." I thought, okay, I didn't even thought about continuing to record them. But I took that advice and I started recording the videos all the time now. So that's just one example. I do pick up nice ideas from what you guys have to say. But I'd love to know what you've liked and what you haven't liked about the class. It helps me for the future. So try to do that by tomorrow. It only takes like 5 minutes to fill out that form. Any questions about anything over here related to what we're going to be doing on Tuesday? Okay, if you think of things, you got lots of chances to ask me questions, obviously. But let's try to tie up this loose end of section 9.5. That is about defective linear systems. We started it on Tuesday. I didn't have a chance to finish it. And if you're the type of person who just likes to read the book and not take a lot of notes, today might be the exception to that, because I am going to do things in a sort of a streamlined notation. So it won't be as lined up with the book as it normally would be. So it would be worth writing this stuff down, or at least, getting notes on this at some point. We had started this example on Tuesday, and I kind of left you hanging with a 48-hour cliffhanger for how are we going to finish this problem. So I want to bring it back and remind you kind of where we left off and pick things up. So we're solving a linear system, and I threw this matrix out at you, which is a 2x2 matrix A. Remember, guys, if it's a n by n matrix, we would need n solutions. So for a 2x2, and they have to be linearly independent. So for a 2x2 matrix, we need 2 linearly independent solutions. And we did some of these calculations last time. The eigenvalues, they are 2 and 2. We have a repeated eigenvalue. And the bad news was that we only got one eigenvector out of it. Yeah, so this eigenvalue, as I like to say, it fails to pull its weight, right? So the eigenvalue fails to pull its weight. We can build one solution, e to the lambda t times v. That's how it's done. So we can build one solution, sure enough, but we need 2 because it's a 2x2 problem. So I have to have a second solution, and this is where the cliffhanger comes in that I made you wait 2 days to get the answer, which is, how do we get x2? How do we come up with a second solution here? And as with many other times this semester that we have seen, the answer is going to be a little bit unsatisfactory. Like, do I really need a PhD to do this? I'm going to guess the answer. And it turns out we're going to guess a solution that has this form right here. You will need to memorize this. So this is the form of the x2 of t. So we have e to the lambda t, no surprise there. But instead of putting an eigenvector next to it, somebody figured out way before I was ever around that we need to use something else instead, namely w1 plus t times w2. And these w vectors, again, this is not the notation from the book, but these w vectors are to be determined. They are to be determined. I'm going to have to explain how you get them. That is coming in these next few minutes, okay? Actually, if you can follow the lecture as to how to get the w1 and the w2, you're good to go. You're going to get one solution, 2 solutions. You got your basis. right? So that's going to be all you need to write down the general solution. And basically it's game over at that point. You're done, right? So that's really where we're at. Is everybody okay with this? Any questions so far? This is just reviewing where we left off on Tuesday. So I'm going to take this box now, guys, and I'm going to plug it back into my system on both the left side and on the right side. I'm going to match them up and see what it would take for the W1 and the W2 to actually work. So notice on the left side of my system, I have to take the derivative. Now this is a derivative with respect to t. You can see that the x2 is a function of t. I'm going to take this derivative with respect to t. Do you guys notice? Do you notice here, guys, there is a multiplication here. E to the lambda t times w1 plus t w2. So to take the derivative, I'm going to have to use the product rule. Whenever you multiply two things and you want to take the derivative, we have to use the product rule. Let's do it. Let's do it. So let's go ahead. I'm going to now plug in to x prime equals a times x. Maybe I should do it on this other board so I have enough room to actually show you the whole thing here. Okay, so let's go ahead. On the left side, I have to take the derivative. So how does the product rule work? I take the first term, which is e to the lambda t, times the derivative of the second term. What is the derivative of w1 plus t times w2 with respect to t? W2. W2. It's like if I ask you what's the derivative of a plus bx with respect to x, the answer would just be b. Right? So in this case, it would just be w2. Okay, and then the product rule has a plus in it, plus the derivative of the first term, that would be lambda e to the lambda t, right? That's the derivative of the exponential part, times the second term, which would be w1 plus t times w2. So all of this here, guys, is just using the product rule from calculus. And now on the right-hand side of the equal sign, I look at what's on the right side of my system here. I simply have a times x. So that would just be a times whatever this proposed guess is, which is the x, e to the lambda t times the quantity w1 plus t times w2. Okay. So far, so good. And my goal, if anybody's gets lost on what I'm trying to do here, remember what I'm trying to do is figure out W1 and W2. Now, the first thing I want you to notice, guys, is that every single term on both sides of the equal sign has this e to the lambda t in it. I'm going to cancel it. So I'm going to go through and cancel the e to the lambda t from everywhere, okay? And then I'm just going to write down what's left. What's left is W2 plus lambda W1 plus lambda t W2. I'm actually kind of multiplying everything out on the left side. And if I do the same thing on the right side, I just have to distribute the A. So we have A W1 plus A T W2. It's going to look like that. Okay? Now, what you notice here, guys, is that some of these terms on both sides of the equal sign have a T in them, and some don't. Some do and some don't. And I'm going to match those up. I'm going to line up the left-hand side and the right-hand side for both the terms that do have T in them, and then also for the terms that don't have T in them. Okay. And by the way, guys, what you're seeing me do right now is just the derivation. There's only about 10 minutes of theory in today's lecture. After that, it'll all be just practicing it with problems. So I'm just trying to derive the procedure for getting W1 and W2. That's all we're doing right here. If I match up the T terms, I'm going to circle the terms that have T in them. Here's one that has a T in it, and here's the other one that has a T in it. If I match those up and set them equal to each other, I would have lambda W2 being equal to A W2. So if I just kind of match up the coefficients of the T, here it's lambda W2 and here it's A W2. And then the other terms that are not circled don't have T in them, and so they should also agree on left side and right side. So what we would have here is W2 plus lambda W1 on the left, and then on the right we would have A W1. And in order to solve for W1 and W2, I am basically going to be trying to solve these two little equations here somehow to figure this out. By the way, does this first equation, so these are the two equations. I'm not going to circle them yet because it's not really the final thing we want. But does this first equation look familiar? A W2 equals lambda W2. We've seen anything like that before? Where have we seen it? Yes, it had to do in chapter 7 with eigenvalue, eigenvector relationships. And in fact, let's write it down. The most important equation in chapter 7 is this one right here. So you don't need to write this. I guess you don't need to write this down in your notes. I'm just refreshing your memory that this is the equation that is relating eigenvalues to eigenvectors. AV equals lambda V. It is the most important equation in chapter 7. I've said that over and over again. So when you're thinking about what's going to happen next Tuesday, you would be shocked if this wasn't there somewhere, right? It's almost for sure going to be something I'm going to ask you about. It's a really big deal. At any rate, here we are seeing that exact same equation, but with W2. So this is really saying that W2 is an eigenvector. So you might be thinking I'm just going to come back and grab my eigenvector and call it W2 or something like that. But it turns out I'm not going to be doing that. I'm not going to be doing that for reasons that will become clear in just a minute. Before I get to that, I'm going to actually take this equation and rewrite it slightly. I'm going to move everything to one side of the equal sign. So I'm going to write this as the quantity of A minus lambda I times W2 equals 0. Okay? Notice that in doing that, I've inserted this I here. That's the usual thing. If you don't put I there, you have a nonsense statement because you cannot take a matrix minus a number. So we have to attach this identity matrix, which doesn't really hurt anything to that equation. So this is one formula that is important to know. And now let's play with the other equation. With this other equation, I'm actually going to do the same thing. I'm going to move everything involving W1 together on one side. So I'm going to factor A minus lambda I times W1. And if I do that, what's left on the other side of the equal sign is actually just W2. It is just W2. So does everybody see that? If I solve this non-T terms formula for W2, if I solve for it, if I isolate it, I have to move the W1 stuff to the other side, and I get A minus lambda I times W1. Now you have a little bit of an inkling as to why I'm not going to just haphazardly choose W2 as the eigenvector we had before, because actually W2 is something you will not be choosing at all. W2 will be the result of having already chosen W1 and then using this equation to determine W2. So how do you get W2? You get W2 after you get W1. You first solve for W1, which I'll explain in a moment, and once you know what W1 is, you then hit it with this matrix, A minus lambda I, and that gives you what W2 has to be. That's how it's going to work. So I find it hard to have these equations constantly memorized. We're actually going to see an even more complicated thing when we go to a 3x3 example. So I have developed, it only took me 10 times of teaching this class to figure it out, I have developed what I think is a very useful diagram to minimize the amount of things you have to memorize if you could just remember the diagram. Here is the diagram that goes with these two equations. I'm going to draw a dot, and I'm going to label it with W1. And I'm going to write the word choose next to it. We're going to choose W1, and here's the diagram, guys. I'm going to draw an arc with an arrow on it, and I'm going to put A minus lambda I at the top of that arc. And the result of that is, according to the second box, supposed to be W2. Let me try to explain what's going on here. This is just my symbolic representation of the fact that you take W1, you multiply it by A minus lambda I to get W2. So these arcs, when I write these arcs, what I'm really telling you, it's your code language for, oh, multiply by A minus lambda I. Now, once I have W2, if I was to multiply by A minus lambda I again, what should I end up with? 0 vector. Yeah, 0 vector. Yeah, that's just 0 there, as you can see from the first box. So actually, we now kind of have a game plan. We have a game plan for how to find our W1 and W2, which is really what this lecture is all about. Okay, that's really the main thing we have to understand how to do. How do we find the W1 and the W2? I think we have a game plan, which is that we're going to choose the W1. Once we've chosen W1, we will not be choosing W2. We will just be computing it using this equation, right? And then we'll be good to go. But how do we have to choose W1? We have to choose W1 so that two things are true. The first one is that if I take A minus lambda I twice and apply it to whatever W1 is, I should get, so look at the diagram. If I start with W1 and I do A minus lambda I twice, if I square the matrix, which is what this is doing, I should end up at 0 on my diagram. And so that's one requirement. The other requirement is that if I only do it once, if I only take A minus lambda I once and apply that to W1, well, on my diagram, that only leads me here. And guys, W2 should not be 0. Actually, if W2 was 0, and we come back over here again, if W2 is 0, that's bad news, because if W2 is 0, our second solution is just going to be a scalar multiple of the first solution. We're not actually creating a linearly independent solution. So what I want to write here, guys, is that if I only do 1 power of A minus lambda I applied to W1, it should not be 0. It should not be 0. Okay? So these are the guidelines. These are the guidelines on how to choose W1. And once I have W1, I'll calculate W2. Let's go back to our example now and try to make all of this work. Let's see how it shakes out. So back to the example. Is everybody with me so far? By the way, by the end of today's class, we'll have done at least 3 of these, so you get into the rhythm of this. It's not so bad. It's not so bad. I do need to calculate A minus lambda I. In the example, the lambda was equal to 2, so A minus 2I. So I have to subtract 2 from the main diagonal of my matrix that I started with, and I get this matrix right here. So lambda is 2. I'm going back to the scratch work in the solution over there. The lambda is 2. We've got our matrix A. We're just subtracting 2 off of the main diagonal. But as you can see, guys, I need more than just A minus lambda I. I actually also need to calculate the square of A minus lambda I. And I would recommend that we do that now. Let's just do it ahead of time. So A minus lambda I squared, which is just A minus 2I squared, would be this matrix times itself. Now, believe it or not, I can tell you, because I've taught the class so many times, I do find that even in week 14 of the semester, there's usually a couple people hanging around that still don't quite have matrix multiplication down. And we absolutely have to know how to do it. So let's just remember we do these dot products like this, right? By the way, the reason I know that is because I grade their midterm threes and I have people that do not calculate these things correctly. I've got to get this right. So let's just check it out. It's just going to be a 2x2 result. And I'm just doing dot products of the rows of the first matrix with the columns of the second matrix. We learned this way back in like week 2 or 3, right? So let's go to the upper left corner. I'm going to have 4 plus -4. Well, that's 0. In the upper right corner, I'm going to have 4 minus 4. That's 0. In the lower left corner, I'm going to have -4 plus 4, which is 0. And in the lower right corner, -4 plus 4, which is 0. Okay. I always get the question, is that always going to happen, that it becomes the all 0 matrix here? The answer is, for a 2x2 system, yes, it will always happen. We're going to do some 3x3 examples in a few minutes, and we'll see some scenarios where that does not always happen. When this happens, of course, this is making our life much easier in terms of choosing W1. Because look at your 2 bullet points that you have to satisfy. The first bullet point says that if you take the square of your matrix and apply it to W1, you better get 0. Well, if this is the square of your matrix, then of course any W1 that you could write down, you could be like totally in a fog. And if you wrote down any vector whatsoever next to this matrix, it will be the 0 vector. I mean, it will multiply together to give the 0 vector. In other words, this becomes automatic. Of the 2 bullet points, the first one would become automatic in this case because the square of your matrix, the matrix itself, is already 0. Guys, once you have a 0 matrix and you multiply it by any vector, you're just going to turn that vector into 0. That's what's going to happen. Right. Okay, so let's review. I am looking for a W1 such that this matrix will kill it, easy, but that this matrix will not. This is the original A minus lambda I. So there are many right answers here. There are many right answers, and I'm wondering if anybody wants to try one out on me. 1-1 would work. It would work. I'm going to choose something even easier than 1-1. Okay, can't choose 0-0. 0-0 is, we actually don't want any of these vectors to be the 0 vector, so we don't want that. But what's easier than 1-1? 1-0. Yeah, 1-1 would have been fine, but 1-0 is even easier. Okay. By the way, one reason that I like using something like a 1-0 is that if you take any matrix and you multiply it by 1-0, you do this little calculation with your matrix multiplication, you just get AC. You just A and C, which is just the first column. In other words, 1-0 picks off the first column of your matrix. So if you're trying to figure out, well, what is W2? It's easy because you just take this matrix, -2, -2, 2, and 2, and you multiply it by 1-0. Well, when you do that, you just pick off the first column of the matrix you were multiplying by, which is nice. You don't really have to do any hard, heavy calculation. You just, at a glance, can write down that column. Does everybody see how I'm getting the W2? It's really from this box right here. I take A minus lambda I multiply it by W1, and that's W2. So my x2 of t, I'm ready to write it down. My x2 of t is e to the 2t times the quantity of W1, which is 1-0, plus t times W2, which is -2, 2. That would be x2. Put a box around that one. Okay, so there you have it. And then if I want to write down the general solution now, I'll do that right here. I don't have a lot of room, but I think I can get it in here. So my general solution, my final answer for x of t Well, it's going to be C1 times X1, which is e to the 2t times negative 1, 1. And then plus C2 times X2, which is e to the 2t times the vector 1, 0 plus t times negative 2, 2. Like that, and that is now the final answer. That would have been the final answer. So I just want to reiterate again that there can be more than one way to write this final answer. If I go back to what Hien said first, his first thing that he said to me was he wanted to take W1 to be 1, 1. So this is like an alternative. We could have done that. If we chose that to be our W1, then when I come here and I multiply this by 1, 1, I would get negative 2 plus negative 2, which is negative 4, and then 2 plus 2, which is 4, and that would have been our W2. So in this case, if we had done this, our W2 would have been negative 4 and 4, and now our second solution would have been e to the 2t times 1, 1 plus t times negative 4 and 4. Just as good of a correct answer as the one we put on the board over here. You might be questioning that, saying, well, how can there be more than one right answer? But remember, guys, in the general solution, you don't just have one solution here. You have an infinite family of solutions that are indexed by C1 and C2. By simply choosing, so if I used this solution and Hien used that solution, and we both wrote down our general solutions, I would have to choose different values of C1 and C2 than what Hien would have to use to make the same specific solution. But it would be possible at the end of the day, when I collect together all possible solutions, we'd have the same list. Of course, they're infinite lists, so you're not really going to be able to by the end of a day, figure it out. But you know what I mean. Yeah. Questions so far? I do want to notice something about the W2. I mentioned earlier that it has to be an eigenvector, because you can see here that A W2 equals lambda W2. Let's go back. What was the eigenvector that we had originally found way back at the start of the problem on Tuesday? The original eigenvector that we found was negative 1, 1. So now look at what we came up with for W2 over here. We came up with negative 2 and 2, which actually is just a multiple of the eigenvector that we had over there. Guys, remember, eigenvectors are closed under addition and scalar multiplication. So if negative 1, 1 is an eigenvector, then so is negative 2, 2. And so this should reassure us that probably we've calculated correctly, because this is an eigenvector. Now, what I often see students doing, and you gotta be careful about this, you cannot just decide, I mean, would it be okay, can I just say, oh, I'm gonna get rid of that, I wanna go back, I wanna use negative 1, 1. This is the same eigenvector that we had over there. The answer is no, you cannot do that, because the W1 and the W2 must be linked together according to this equation here. If you change this W2 and say, oh, I know it's gotta be an eigenvector, so I'll just use the one I found in the first place, that is not going to be compatible with this W1. You see what I mean? If you're going to cut this one in half, you would have to then cut this one in half to sort of keep them balanced. I don't recommend doing that. Just live with the W2, whatever it comes out to be. You don't have to edit that. You don't have to change it. It's just fine that it is in this form right here. Yeah. Okay. So I thought I'd mention that. But it is good to see that W2 is an eigenvector. Everybody with me so far? Oh, I love this stuff. Everybody always asks, oh, what's your favorite part of 250B? My answer is always, oh, whatever I'm talking about that day. I really do like all of this stuff so much. Okay, guys, I want to talk about 3 by 3 examples for the rest of what I want to say in this section. So let's look at some 3x3 defective systems. By the way, so I did one 2x2 example, but the more intricate ones are the 3x3s. By the way, the first thing I'm going to tell you about the 3x3 defective systems is that that's as high as I'm going to go. So just as a note here, no 4x4 or larger systems in this class. I'm not going to go there. You can sort of see partially why I wouldn't go there. If I was going to do 4x4 systems, then instead of multiplying 2x2 matrices together, I would be multiplying 4x4 matrices together. That's already a headache, 16 dot products to just calculate that. It just gets too hard to do it by hand. It's not that you can't do it. It's just to do it by hand would be, I think, asking a little bit too much. So I'm going to stick with 3x3s or smaller, which actually has a nice little side benefit to you, which is that because my systems are defective and they're only 3x3, I can guarantee you that in this section, you will not see any complex numbers. Why do I say that? Why couldn't I have complex eigenvalues if I'm in a 3x3 defective system? Go ahead, Arlene.
Because complex conjugates, it would be impossible if we have 3 eigenvalues. Because
yeah, so if I have a
think
3x3 system, how many lambdas do I have?
3.
3, right? If I have a defective matrix, don't I have to have repeats? So if I had a complex conjugate pair like this, I would actually have to have it twice, right? You'd have to have it twice. Well, now how many lambdas is that? 1, 2, 3, 4. That's too many lambdas for a 3x3 matrix. So you're never going to see that. So the whole thing we learned on Tuesday with the Floy method and all that stuff with sines and cosines, you're not going to get that as long as I keep my promise that the matrices would not be larger than 3x3. You can see this would be a mess if the matrices got larger to do it by hand. And I don't need to have you guys stress about that because in the real world, you'll have all the time in the world if you have larger matrices to put them into a computer system and let that do the job for you. So let's stick with 3x3s. Even 3x3 systems is enough of a challenge as it is because there's actually several cases that can happen. And I'd like to write them down for you. So I'm going to make maybe 3 columns. I'm going to make sort of 3 columns here, but I'm going to have to use sort of 2 boards to do it. So I'm going to give you some cases of what could happen, and maybe you guys will be thinking of these as well. I think I'll do case 3 over here. So one way that you could have a defective 3x3 system would be you have a lambda value, say lambda 1, and then you have another lambda value, lambda 2, but it got repeated twice. And then maybe lambda 1 gives you V1, but the lambda 2 fails to pull its weight, and it only gives you 1 eigenvector, which we're going to call V2. So that would be bad news. You only have 2 eigenvectors for this 3x3 matrix. So it's defective. Well, so the question is, how are you going to write down your solutions now? Because if it's a 3x3 system, you must have 3 solutions. Okay, over here we only needed 2 because it was a 2x2 system. But this is a 3x3 system. I need 3 solutions. Well, I have a proposal for you. I always do. The proposal is x1 of t is just going to be e to the lambda 1 t times v1. That's the first solution. And then my second solution is x2 of t. This is going to be e to the lambda 2t v2. No problem with that. But now for the third solution, I'm going to have to use those w's again. Same W problem as before. So this will be e to the lambda 2t times W1 plus t times W2. So that seems promising. Yeah, that's pretty promising that that's going to work for us. Okay. I like to call this scenario, I like to call this the mixed eigenvalue case. And by the way, this is mostly just my terminology. It's not necessarily all that standard, but this is the mixed eigenvalue case. You have different lambdas, but the one that was repeated did not pull its weight. Okay? Can somebody give me another scenario of sort of eigenvalues and eigenvectors where we would have a defective case for a 3x3? Brody?
All three being the same?
Yeah, we could have the same lambda 3 times. Definitely possible. And maybe those repeated lambdas only give us 2 eigenvectors. Okay, that would be another possibility. And in this case, I'm going to kind of do the same thing I did before. x1 of t, I'm going to come up with my 3 solutions. E to the lambda t times v1. And then my second solution is going to be x2 of t equals e to the lambda 2t times v2. And again, just like before, the third solution would have to be using the w's. So e to the lambda t times the quantity of w1 plus t times w2. And for all of this, we're still going to be using the same diagram. It's the same diagram, the same rules on W1 and W2, right? All of the stuff that's over here still applies even in the 3x3 case in terms of how you come up with the W's. Okay. By the way, I like to call this one the regular defective case. This again, it's just my terminology for it, just so we can talk about it. All right. Is there a third case? Well, there must be. I wrote it on the board. There must be a third case. Is there another scenario of how we would possibly end up having a defective 3x3 system? I'll give you a hint. The name for this one is going to be super defective. Like, what could we have that would be really badly defective? Go ahead, Seth.
3 of them, but only 1 vector.
Yeah, what if you had the same lambda 3 times and you only managed to get 1 single eigenvector out of it? That's super defective. That is super defective. So in this case, the question becomes, well, how do we write down 3 solutions? Well, as before, I'll start off. x1 of t can just be e to the lambda t times v. Okay, so I've already run out of easy solutions, so I'm going to go to my w's right away. So x2 of t would be e to the lambda t times w1 plus t times w2. And now we have to figure out how to get a third solution. We have to have 3 of them, guys. We have to have 3 solutions for a 3x3 system. So the question is, what is x3 of t? Well, at this point, somebody has to come up with another guess that has to be plugged back into the linear system on both sides and then solved for. And I'm going to spare you the derivation of it because it's almost the same derivation that I've already showed you in that 2x2 example. But here is what it is. So we'll just write this down. You do need to learn this, though, by Tuesday. E to the lambda t times the quantity of W3 plus t times W4 plus t squared over 2 times W5. Oh my goodness. That's what it actually is. And of course, what in the world is W3, W4, and W5? Well, there's a diagram for it. And I'm going to go straight to the diagram this time. The diagram looks like this, guys. So for this last solution, we're going to choose right here. We're going to choose W3. And when we multiply by A minus lambda I, again, I'm not showing the derivation. It's very similar to the one that I just showed you earlier today, though. I follow that first power of A minus lambda I, it carries me over to W4. And then if I follow it again, another A minus lambda I brings me to W5. And if I go one more time, A minus lambda I for a third time, finally now I get to 0. I finally get to 0 here. Yeah, so it's a slightly bigger version of the diagram we were using earlier to get the W3. So let's write down kind of a 2 bullet point summary of how to choose this W3. So choose W3 so that, let me write down my little bullets here. If I start with W3 and I power 3 powers of A minus lambda I onto it, I end up at 0, right? So what we're saying here, guys, the first bullet point is that A minus lambda I cubed of W3 should take me to 0. But if I only take 2 powers of A minus lambda I, so if I start at W3 and I only hop 2 times to the right, I end up at W5. I do not get to 0 yet. So this is not 0. So as you can see, guys, it's very similar to the way in which W1 was chosen in the earlier scenario. This W3, W4, W5 business, it only comes up in the super defective case. As you can see, in cases 1 and 2, you don't need it. You can get your 3 solutions without it. It's only in this case where you absolutely need it. That may have you believing that the super defective case is the hardest one of these 3 cases here. But I have a feeling, if you guys are feeling the same way that I am by the time you see all of this, that this is actually the hardest case, I believe. That the mixed eigenvalue case is the hardest case. And I'm going to show you why, because I'm actually going to do an example of a super defective case and a mixed eigenvalue case. They look quite different. And there's challenges with both of them. Really, the challenges on the super defective case is you just have to remember all these. You have to remember the formula here for the X3. The process, if you get this diagram down and you understand it, it's not that bad. It's really just a higher version of the one that we had from before. But yeah, let's just do an example. I think I'll do a super defective example right now, then we'll take a 10-minute break, and then we'll do the mixed eigenvalue example, okay? The easiest case is probably the regular defective. This one, you don't need the W3 through W5, and also it's pretty easy to get the W1 and W2. So case 1 and case 3 are probably the hardest ones. On the homework that you're doing for tomorrow night, I think there's at least one example of each of the 3 cases. So you will get to practice this for the homework. Okay, so let's do an example. So to get my matrix out, I forgot what the exact matrix was, but oh, here it is. Yeah, so let's do this example. Let's solve x prime equals a times x, where a is equal to this matrix here, guys, -1, 1, and 0. And then -2 and -3 and 1, and then 1 and 1 and -2. And I'm going to give you a hint. I'm going to give you a hint that lambda1 is -2 and lambda2 is -2. So this is going to be the setup of the problem that we're going to solve right now. Let me get this over here as we get started on this. Seth.
Is there no parameter for A minus lambda I time just normally like I squared?
Correct, yeah, if we have said that this is not zero, then the first power of it for sure is also not zero. So you don't need to actually write that one down. That's good question, good point. Any other questions so far? The reason that I'm giving you these lambdas here, and I've been known to do this on my exams too, if you have the lambdas wrong, oh, it's such a nightmare, right? The eigenvectors becomes really not making any sense. So it's really nice if we have the lambdas given to us. This matrix has very few zeros in it. And as such, there is not really a good row or column to do the cofactor expansion on if I was going to actually try and work it out from scratch. So I'm just trying to make your life a little easier here by at least giving you 2 of the lambdas. Why did I not give you the third lambda? There's supposed to be 3 lambdas, right? What would happen if I only gave you 2 of them? You can solve for the third one. You can solve for the third one how? The fun facts. The fun facts. If you add up all of the lambdas, it has to add up to the trace of this matrix. What is the trace of this matrix? -2 plus -3 plus -1, that's -6. So far, the first 2 lambdas are adding up to -4. So just from that trace fact, we actually know that the third lambda is also -2. Let me just say this is from the fun facts. So you definitely want to know those fun facts. It's very, very helpful, especially if I give you partial information about the eigenvalues. Okay, so I have the lambdas, and we have the same lambda 3 times. Let's go ahead and do the null space for that. So we always have, we're always trying to find the corresponding eigenvectors now. So I'm going to subtract -2 from the main diagonal. So in other words, this matrix will end up being A plus 2i. So I'm subtracting -2. This is the same thing as adding 2. So if I add 2 to the main diagonal of my matrix, I'll get 1, 0, 0, -2, -1, 1, and 1, 1, 0. Now, as we've learned many times before, this matrix is never invertible. We have to be able to cross off a row. And in this case, I'm going to cross off the third row because I see that it's the same as the first row. So I'll get rid of that third row. Here are my unknowns if I want to kind of write this down in terms of X, Y, and Z. But we need to do an ERO, it looks like. Wow, it's been a while since I've done that. I'm gonna take 2 times the first row and add it to the second row to get a 0 below this 1 here. So here's my pivot in the first row. I have 1, 1, 0. And then if I take 2 times the first row and I add that to the second row, I get 0 and 1 and 1. Okay, and like I said, I've already gotten rid of the third row. It's just all 0 basically. So this is just practicing our EROs, and we're just solving the system here by Gaussian elimination, right? Back substitution. My free variable is z. Third column does not have a pivot, so z is free. So I'll call that t for the time being. And looking at the second row of my matrix here, guys, you see that y plus z should add up to 0. Y plus z should add up to 0. So if z is equal to t, what does y equal? Negative t, exactly. Exactly. And then if I go back and look at the first row is telling me that x plus y adds up to 0. So what would x have to be equal to?
T.
Just t again, right, exactly. So x plus y cancels out as well. So there you go. And now we bust out our variable here. So I'm going to go ahead and write down my vector. If I bust out my t, I get my eigenvector of 1, -1, and 1. So just get rid of the t by busting it out. And guys, this is super defective. The same lambda 3 times, and we only came up with 1 eigenvector. So let's just make it clear. This is the super defective case. I'm starting right off with this example first. Okay. We can write down one solution. So I can write down the, let's see, the x1 of t would be what? E to the negative 2t times this vector 1, negative 1, 1. I will go ahead at least and get that much down. That's the first solution. Okay? So far, hopefully so good. Now, because it's the super defective case, we're gonna need 3 powers of A minus lambda I. I'm gonna calculate those powers first, just to get that done first. I like to do that first, get it out of the way. So we're gonna calculate the powers of that. Yeah. Let's come back over here. Very important. When you are squaring and cubing your matrix, make sure you are not squaring and cubing the row echelon form of your matrix. You actually need to take your matrix before you butchered it with EROs. Okay, so we're gonna take the one here and we're gonna square that one and cube that one. Right, so let's go ahead. This is just gonna be some calculations here. A plus 2I squared, we will need to work this one out. I'm going off of what we have over there. We have 1, 1, 0, and then negative 2, negative 1, 1, and then 1, 1, 0, and we're going to multiply that by itself. Okay, so here we go. We're going to have to do 9 dot products to get the result of this. And if there's anybody out there who's still feeling like, oh, I don't really know matrix multiplication, don't hide in the shadows with that. Like, if you need to come talk to me about it, I will not jump down your throat over it. I will help you. I want you to leave this class knowing how to do this. Like, occasionally somebody tries to go the whole semester without really figuring it out. That's just not a fun place to be. So if you need help with this, let me know. But I'm going to just go fairly quickly for right now, dotting these rows with these columns. So in the upper left corner, I have 1 minus 2 plus 0. That's negative 1. And then in the top middle, I have 1 minus 1 plus 0, which is 0. In the top right corner, I have 0 plus 1 plus 0, which is 1. I'm going fairly fast for right now, just because I don't want to dwell on the calculation here. On the middle row, I have negative 2 plus 2 plus 1, which adds up to 1. And then in the middle entry, I have negative 2 plus 1 plus 1, which is 0. And then in the right entry of the second row, I have 0 minus 1 plus 0, which is negative 1. And we get to the bottom row now. We do the same thing one more time. 1 minus 2 plus 0. That's negative 1. In the middle, I have a 1 and a minus 1 and a 0, which adds up to 0. And finally, in the bottom right corner, I have 0 plus 1 plus 0, which is 1. So that is A minus lambda I squared. And then, as if that's not bad enough, we actually have to cube this matrix as well, because you can see that that is going to come up right here. So if I cube this thing, I am going to skip putting everybody to sleep with this and just tell you what you get. Actually, you are going to get, in this case, all zeros. You can check that. It turns out that in the super defective case, which is really the only case where you really need to cube the matrix at all, you will always get the all zero matrix to come out. And in fact, that is actually why I say that this case is easier than the mixed eigenvalue case. What makes it easier, guys, is that because of this is good news. This is good news because it means choosing W3, you got 2 requirements here. Well, that one's automatically true, right? Because the cube of A minus lambda I is already the zero matrix. So you'll have no trouble choosing your W3 for this. But it'll be this one that you have to think about a little bit. You need to choose a W3. Let me just say it this way. You need to choose a W3 that will survive this matrix, but not survive this matrix. Of course, nothing survives this matrix. So it's really this one you have to worry about. Some of you might be wondering, well, why are you talking about W3 already? What about W1 and W2, right? Where's that in this whole conversation? Well, I have an answer for that too. I have an answer for everything. I ask questions to myself and then I answer them. Take a look at my W3, W4, W5 diagram. Would you guys agree that if I sort of just ignore, or if I sort of just cross off the first arc, I just kind of ignore the one on the left, you see what you're left with? So here I have W4 going to W5 going to 0, just that much of it. Compared with the original diagram that we have over here, do you see that actually you could just put the W1 in the role of W4, and you could just put the W2 in the role of W5. So actually, I am going to figure out the big diagram. I'm going to figure out W3, W4, and W5, and then I'm just going to say, look, W1 can just be the same as W4, and W2 can just be the same as W5. That's the way I recommend that you do it. It saves you some time and some work. So I need to choose a W3 right now, guys. I need to choose, I'm going to skip to W1 and the W2 for a minute, and I am going to go to the all-important question of choosing W3. But question first.
When you're doing the cube, does it matter which order you multiply by?
No, you can take this one times the original, or you can take the original times this one. Yeah, good question. Yeah, exactly. Okay, so guys, is there anybody out there who's brave and wants to try to give me a vector here that will survive this matrix, but will not survive this matrix? Actually, tons of right answers. Does anybody want to try one on me? To make it real easy. Go ahead.
1, 0, 0.
I would choose 1, 0, 0. Absolutely an easy choice. It's an easy choice. Guys, if you have, why do I like 1, 0, 0 so much? You know, if I have just any old random 3x3 matrix and I multiply it by 1, 0, 0, what happens when you do this calculation is, if you just look at it, you end up just picking off. So this is A plus 0 plus 0. That's A, right? And then D plus 0 plus 0 is D, and G plus 0 plus 0 is G. You just pick off the first column of your matrix. So if you can see that the first column of your matrix is good to go, it's not 0, then that's a good choice to use. Now, just to be a little bit cautionary here, guys, you can't be too sort of careless with this. If you had chosen 0, 1, 0, which isn't that far off of 1, 0, 0, this vector would not have worked because 0, 1, 0 would be picking off the middle column, not the first column of your matrix. And I don't want the middle column. Guys, it's supposed to be not 0 when I take W3 and hit it with the square of A minus lambda I. So we cannot choose 0, 1, 0, but 1, 0, 0 is great. 1, 0, 0 is great. Is everybody following me on this? This is the hard part. It's just choosing the W3. And there's lots of right answers here, but once you've chosen W3, it should be pretty easy to get the rest of our W's. How do we get W4? If we forget, we go back to our diagram. Starting from W3, we just multiply by A minus lambda I. A minus lambda I is actually this matrix. This is the original A minus lambda I. And if I apply 1, 0, 0 to this matrix, as I just showed you a moment ago, it picks off the first column, right? So W4 becomes what?
1, -2, 1.
1, -2, and 1, yeah? Absolutely true. Everybody with me on that? That's the first column of the matrix over there where it says the word null space. And now I want to figure out what W5 is. Guys, there are two ways to get to W5. And I'm going to give you a choice. my first class was almost a 50-50 split on which way they wanted to do it until I explained what the better way was. So if I want to get to W5, I can either take W4 and multiply it once by A minus lambda I. Or I could choose to go back to W3 and multiply 2 times, which is the square of A minus lambda I, and that will sort of directly take me from W3 to W5. So we can either calculate W5 starting from W4, or we can go back to W3. See what I mean? How many people would prefer to go back to W3 and calculate it from there? Raise your hand if you think that's the best way. Okay, it's about half the class. How many people would prefer, since we already have W4, just take W4 and just apply one time the A minus lambda I? Couple brave people here. Okay, yeah, actually, so here's the important thing. There is no wrong answer to that. You can do it either way, you'll get the right thing. But you know what I love about the W3 vector? Is that it is 1, 0, 0. So if I multiply that onto the square of A minus lambda I, I'm immediately going to get my answer. Whereas if I take W4, here's W4, that's fine, but I would be multiplying W4 not by this matrix, but rather by this one then, right? This is the A minus lambda I, and you would actually have to like do the math on it. It would be harder work, I think. So my preference, guys, is to go back to W3. It's not wrong to take W4, but gosh, I just love the fact that I can write down W5 straight off of that matrix. So I would recommend doing that. And then, as I explained earlier, we can just choose the W4 to be W1, and we can just choose W5 to be W2. And at this point, I can write down my my other solutions. So x2 of t, that is going to be e to the lambda t. Now lambda was -2, so this is e to the -2t times the quantity of W1, which was 1, -2, 1, plus t times W2, which I've relabeled with W5. And so we put -1, 1, -1 there. That's going to be x2. You okay, Joe? Okay, just making sure. So that's x2. And then for x3, I can go ahead and do x3 as well. x3 of t is e to the lambda t, lambda being -2, times W3, which is 1, 0, 0, plus t times W4, which is 1, -2, 1, plus t squared over 2. You do have to memorize this, guys. T squared over 2 times W5, which is -1, 1, -1. So here, my friends, are the x2 and the x3 for my system. Okay. By the way, you probably remember that the W2 was an eigenvector. It's the last vector before you get to 0. Same thing for W5. It's the same vector. It's an eigenvector. Let's just check that. Is that true? Look at what we got for W5. And then look what we got originally way back over here for our eigenvector. And do you see that they're not quite the same, but they're just off by a minus sign? They are scalar multiples of each other. That is really reassuring that our W2 and our W5 really are eigenvectors, but we're not going to tweak these now. We're going to leave them as is, even though they're not the same as the V over there. We're going to leave these things as is because these diagrams, I guess I lost part of this diagram. These diagrams really link up the W's in a rigid manner that you can't just start tweaking parts of that diagram without tweaking the whole thing. So just leave things as you find them on this, guys. You don't need to get fancy with doing any kind of changes. So then my general solution My general solution for x of t would just be C1 times x1 of t plus C2 times x2 of t plus C3 times x3 of t. And it is actually okay with me if you want to do this next week on the test. If you've figured out x2 and x3 and x1, which was way back over here, if you've already written them down, I don't need you to like recopy them all out again. It'll take you more writing than you really need to do. But do put down the general solution. I want to know that you are aware that you have these constants and build this linear combination. Okay? What do you guys think? This is the super defective case. Super defective. It's really all coming from this diagram. One thing to remember, guys, is none of the W's, let me say this loud and clear because I've seen it before. None of the W's should ever just be 0, 0, 0. W3 shouldn't, W4 shouldn't, W5 should not. None of the W's are ever the 0 vector. That's always a red flag. And you can see here that we were good with that as well. Okay, I think we should take a, sorry, Seth, go ahead.
But the cubic one is always the 0 vector.
This matrix will always be all 0, which makes your job of choosing W3 easier. Now, after we take a 10-minute break, I'm going to do a mixed eigenvalue example, and that's where that one gets tricky because it turns out that the highest power of the matrix you're working with is not necessarily all 0. We have to be a little more clever there, and I'll talk about that when we get to an example of it. Let's take 10 minutes though. Maybe you need to decompress, grab some fresh air, grab some water, go run around the building 10 times. Whatever you need to do. And in 10 minutes, we will resume.
That's right. You're really, it's so down. I'm so slow. I do my Uggs.
Oh, your Uggs on? Okay. You do 10 laps of those.
No, that would hurt my feet so bad. Yeah, I am.
This guy?
I'm just okay.
This guy, I know, just want
Just pay attention. Just pay attention, bro.
Not doing other studying.
The last
Oh, this one. Oh, so
How rigorous
I
are you when you study?
just handed that to you guys. I basically said that some genius, maybe for me, figured out that.
No, I just gotta take some photographs and it's already engraved.
So I failed this score.
Yeah, right here. Feel reliable, right? These bad boys?
Yeah, so I didn't explain like where this is from. I just handed this, it turns out if you take this sheet and you do the derivative of it, and then you compare it with any times this, you can match up the
You get it?
terms.
Oh,
of the non-key terms.
Yeah, huh? Light work.
And you derive this diagram.
Basic math.
I mean, as long as you remember the formula and how to do it, it's all good. That's easy, bro. No, matrix multiplication is the easiest thing, though.
Oh yeah, guys, if you have questions on the homework from 9.4, feel free to write any problems up on the board over here that during the break that you would like me to.
And go get some sun.
Go get some sun.
Go get some sun.
Get some sun. Buy some grass.
Put some grass. There's no grass around
Make some grass. Where y'all going? Wait, I wanna go to. What? I ain't that bad. I wanna tag along. I wanna be. Oh. So you're just. I don't know, but just don't mess with this. Yeah, oh, the one with the line, actually. I got that. Actually, a message. And that's, I guess, this question. You know. I just. Here you go. I don't think they, they reach out to, I think. I think, I'm in the process of doing like phase 3. Which is. Like, so that's a one great deal. Yeah, we want to be able to see what we can. After I finished my. I'm guessing it's not data sets. Well, like, 'cause they still have that.
Yeah. So before you leave it.
Like, I was so sketchy. I was like, exactly like this. Yeah. I'm like, there's something not big. So I'm.
Do I even know how to do this? That'd be the worst thing ever.
That's pretty common. Either look at that one or look at that. Yeah, I don't think it would have been like too much. Well, I would have sketched, but I was verified. I'm like, okay, we're gonna be one thing. And then you look at the website, I'm like, okay, like I asked that. Because this is a real link.
Okay, watch me. Oh, okay, you're on this like, that's what you've And so you're not all this.
I just get down like all the data and I like.
And not great enough.
You don't know what it is, but it actually. We all want to go with her.
Like, I would rather do it.
The two part.
Like, I think basically.
I'll ask her, she went so many. I'm like.
That's like, I think that. And then I'll. Like, I'm not really as easier.
Be fun.
Honestly.
She was in the city. It's a different one, though, because the one very usual, it's a different. You can reserve it next time.
Yeah, it's fun sometimes, but it's like a mini. Like, I'm back in the days. We lost. I won with the quiz.
Yeah, pop quiz.
Oh, yeah.
We're at 17 points.
Oh, no.
I think he did that one time. He's like, oh yeah, we're gonna have a pop quiz.
Oh, yeah.
Remember he did that to us?
I think it's the other first group that we have.
Yeah. Dr. Anna, remember the time you scared us when you gave us our first group quiz and you're like, and then we're all like
25% of your grade. I would like to see my students squirming.
that's funny. Yeah, we're all scared.
I can't get away with that anymore. You guys, when I pass papers out, you know it's not really a quiz.
Yeah.
I do need to send out an extra credit quiz.
So.
I'll send that out through Canvas probably Friday, somewhere around when the homework is due. Yeah, over the weekend you can work on it. Yeah. All right, everybody, I think almost everybody has made it back, and I'd like to pick things up again where we left off. During the break, I passed out a little group work onto your table there. We are not going to have time to do this one probably today. All of the other group works, we did do them in class, which is great. This one you might have to kind of just browse over on your own. The solutions are in Canvas, and I just recommend when you have sometime between now and Tuesday that you just kind of look at those problems. There's nothing too crazy about any of those questions there, but it'll be kind of use it as like a little mini review, I guess you could say. But we may not have time for the group work because I do want to answer a homework question or two. And before I do that, I want to make sure we do one more example of these defective linear systems. So I've got it already written on my board up here, and I'd like to just sort of take it from the top. This is a system x prime equals ax. And I have a 3 by 3 matrix A right here. As you can see, 2, -5, 0. And the second row is 0 and 2 and 0. And the bottom row, -1, 4 and 1. Okay, so I'm going to try to solve this. And the very first thing I have to do is what? For any kind of problem like this in the entire chapter, since we started the chapter, what's the first thing we need to do?
The eigenvalues.
Find the eigenvalues. Thank you. Yes, exactly. So the solution, we're going to start off. And guys, there's a lot of steps here. So don't give up on yourself. You're like, oh, I don't know how to do the problem. Well, you might know how to do part of the problem. And if you start the problem and start getting the juices flowing, I wouldn't be surprised if somebody can get unstuck just by kind of going through those motions. So try to give yourself a good chance at it. Let's just start off by doing the characteristic equation. I'm going to subtract lambda from the main diagonal of this matrix. So everywhere I have entries on the diagonal, I subtract 1. Otherwise, I leave it exactly the same. Okay? So we'll get something like this with those lambdas subtracted off of the diagonal. Any suggestions about how to actually do that determinant? Cofactor expansion, right? This time I didn't give you any hints, right? There's no hints about the eigenvalues. Which row or column might be good for expanding this one?
Column 3.
Yeah, we could use column 3. You could also use row 2. Either one would be pretty effective. I'll just go ahead and stick with column 3. I think that sounds fine. If we look at column 3, we have nothing in the first entry, minus nothing in the second entry, and then plus the last entry, which is where all the action is. I have a 1 minus lambda here. And if I cross off that row and column and I take the minor in the upper left corner, that minor is going to have 2 minus lambda times 2 minus lambda, and then actually that's it. You subtract 0 from that. So it's actually, believe it or not, pretty easy. It's already factored. It's actually already factored, so we don't have to do any more algebra. We're just going to set this equal to 0 like always. And once we do that, we see right away it's just this times this times this equals 0. So lambda is equal to 1 or 2 or 2. Based on that, do we know yet whether this matrix is defective or not? We don't know, other than the fact that that's what this lecture is about. But on the exam, it's not going to say, oh, this is defective, or you're going to have to figure that out. The repeating of this lambda means it might be defective. It might be defective. We have to go a little further into it to decide for sure. So I'm going to focus on that lambda first. I usually, whenever I have repeat lambdas, I usually start with those. So let's take lambda equals 2. I'm going to do a null space here of the matrix. Now the matrix I'm going to write down here, guys, is A minus 2i. So the A minus lambda I is what we have to write down. And that means I'm going to subtract 2 from the main diagonal of A. I'll have a 0, a -5, and a 0. The middle row gets completely zeroed. And the bottom row is -1, 4, and -1. Okay. Of course, as always, this matrix is not invertible. And we cross off a row, we see a row of zeros. If you see a row of zeros, you have to cross that one off and use that as your freebie. And then I'm going to just quickly do an ERO here, a couple of EROs at once. I'm going to move the bottom row to the top row, and I'm also going to do a sign change on it. So I'll take the bottom row and write it as 1, -4, and 1. And then I'll take the top row and I'll put it into the middle, but I'm going to take the -5 and divide it by -5 and make it into a 1. Okay, this is just getting row echelon form here. And so we have our two pivots, as you can see. The unknowns, x, y, and z, line up with those columns like always, and my free variable would be z. I'll call that t, which is free. As I look at the middle row, I see that 1 times y has to add up to 0. So actually y is 0. That is the conclusion from that middle row. And if I go back to the top row to solve for x, notice that x minus 4y plus z is 0. But the y was already 0. So that's really just x plus z. X plus z is 0, so that means x has to be -t. -t. And so sure enough, the vector, when I bust out the t, the vector that we get, the eigenvector, is -1, 0, and 1. And so do we now know if this is defective or not? Roman, is it defective or not defective? It's defective, isn't it? Yeah, because the same lambda was here twice. 2 and 2, but we only got one eigenvector. It did not pull its weight. Yeah. Guys, I really love seeing you studying chapter 9 with chapter 7. They kind of go together. There's so many common threads between them. And together it's going to be about half of your midterm. So it's a big chunk of it. So here we go. We can write down one solution immediately, which is the x1 of t. I'm going to come over here and write it down. It's going to be e to the 2t times the vector -1, 0, and 1. Just like so. Go ahead and put a nice box around that so I can find it easily. That's one of my solutions. Now, to get my second solution, I have to use the w's, right? So let's just remember, x2 of t is going to be e to the 2t times w1 plus t times w2. And the way I like to work on something like that is I like to draw the diagram first. So I have my w1, and then there's the diagram has this arrow hopping over to w2 with a minus lambda I being the matrix that you're multiplying by. And then if I do it one more time, a minus lambda I again, we get w3. By the way, this is defective, and we can see that this is the mixed eigenvalue case. We now know of the 3 cases, this is the mixed eigenvalue case. This w3 shouldn't have been there. I'm sorry, it should be a 0. There is no w3, w4, or w5 unless it's super defective. Yeah. Yeah. Not really, no. Other than the fact that, so remember the W2 basically becomes W5.
Yeah.
And you could say that, yeah, W3 does hop over to W5 after 2 steps. So in that sense, you could.
Directly.
No, not really, not direct. Yeah, not direct, yeah. Okay, so this is the diagram, right? Everybody got that? So I'm going to choose W1. And then I'm going to calculate W2 from the diagram. And to choose W1, I need to choose it so that it will survive this matrix here. This is A minus lambda I, but it should not survive 2 powers of the matrix. Let's calculate 2 powers of this matrix. So what is A minus 2I squared? We are going to need this. So A minus 2I is 0, -5, 0, and then 0, 0, 0, and then -1, 4, and -1. I have to write it down side by side, 2 copies of it, because we're going to square the matrix here in just a second. That's going to look something like so. And this is going to be more matrix multiplication, yeah? We dot the rows of the first matrix with the columns of the second matrix. There's going to be 9 numbers to calculate, and I'm going to do it pretty fast. Okay, so starting in the upper left corner, we're going to go across and do these dot products with the first row. So 0 plus 0 plus 0, that's 0. And then in the middle entry, 0 plus 0 plus 0 is 0. And then the last entry, 0 plus 0 plus 0 is 0. So that's all zeros. The second row is easy to see, it's all zeros. And then if I do the third row, I have 0 plus 0 plus 1. So we get a 1 there. And then in the bottom middle entry, I have 5 plus 0 minus 4, which is also 1. And then in the far bottom right corner, I have 0 plus 0 plus 1. So there is your matrix. It's got a row of 1s on the bottom. So now we get to the tricky part of the mixed eigenvalue case. This last matrix that we just calculated is not all 0, which means it's not quite as easy as the other cases where you said, oh, every vector would be killed by this matrix. In fact, this matrix will not kill 1, 0, 0. So that's not going to be a good choice for W1. If you put 1, 0, 0 next to this matrix, you will pick off the first column, which isn't 0, right? Remember, guys, whatever you choose here has to become 0 when you hit it with that matrix. So 1, 0, 0 isn't going to work. But neither is 0, 1, 0, because that would pick off the second column of the matrix, which is not all zeros. And neither would 0, 0, 1, because that would pick off the third column of this matrix. No column of this matrix is all zeros. This is the first time we've seen this today. This is the first time today that we've seen that the matrix that we are using to build our chain on this diagram, this last matrix, has no columns that are all 0. So choosing W1 suddenly becomes a bit of a challenge. And I'm wondering if anybody thinks they can give me something. So 1, 0, 0 doesn't work, 0, 1, 0 doesn't work, and 0, 0, 1 doesn't work. Does somebody want to try me on something slightly more clever than that would work? Set.
1, -1.
1, -1, 0. This works so well when you kind of know how these dot products work, right? Why is that going to be a good choice? Well, if you put 1, -1, and 0 next to this matrix, and you work it out, the bottom row does give you 0, 0. Well, it gives you 1 plus -1 plus 0, which is 0. So that does work. You see, basically, you have to use 1 and -1 here to get these two to cancel. Now, this is still not the only right answer, right? We could have chosen 0, 1, -1, right? Or we could have chosen -1, 0, and 1. There would have been a number, or I could have chosen 100, -100, and 0. The choices for W1 can be quite extensive, but in this case, we can't just get away with a standard basis vector. Let's choose this. Let's take Seth's proposal, and then let's try to figure out W2. Now, to get W2, we have to hop one step on our diagram from W1. That means I have to take W1 and put it next to A minus lambda I. So for W2, actually, sorry, let me do it this way. Let me actually write out my matrix here: 0, -5, 0, 0, 0, 0, and -1, 4, -1. And I'm going to put Seth's vector 1, -1, 0 next to that. And if we calculate this, we should figure out W2. So let's do it. We have 0 plus 5 plus 0, which is 5. The middle row just gives me 0. And on the bottom row, I have -1 plus -4 plus 0. That adds up to -5. That's your W2. Okay, and so my second solution to my system then, guys, my second solution is going to be e to the 2t times the quantity of W1, which is 1, -1, 0, plus t times W2, which was 5, 0, -5. There it is. There it is. By the way, notice the original eigenvector over here was -1, 0, and 1. Look what happened when we calculated W2. We got an eigenvector. In fact, it's a scalar multiple of the vector we had over there. We're getting that right here. So that is not surprising. We would have expected the W2 to be an eigenvector, which means it should be a multiple of the one that we had already found. So far, so good? That's the guts of the problem. We still do have one other solution to find, which is the one that corresponds to lambda equals 1. I will go fairly quickly through this part because this is just the standard process of finding an eigenvector here for this eigenvalue. But we do have to do this one. This means we take a null space. And I'm going to go back to the very top, the original matrix A, and I'm going to subtract 1 off of the main diagonal of it. So I'll get 1, -5, 0, and then 0, 1, 0, and then -1, 4, and 0. Oh, is that right? Yeah, I guess that's right. Okay, I guess that's right. Yeah, this is right. Guys, we know that this matrix is not invertible. Cross off a row. I actually already have nice pivots here in the first 2 rows, so let's just keep that. We'll cross off the 3rd row, and if I line up my unknowns here like I always do, z is going to be free, so I'll call it t like always. The middle row immediately tells me that y is equal to 0. And once y is 0, then the first row will tell me that x is 0. Again, I'm going kind of fast through that, but it's just Gaussian elimination. Same thing we've been doing since the 3rd week of the semester. And we now write down our vector v by busting out the t. So we would get 0, 0, and 1 here for this vector. Great. And so now I can write down x3 of t, which would be e to the lambda. This time lambda is only a 1 times t, and then the vector 0, 0, 1. So here's your x3 right here. Get a nice box around that as well. And that's our 3rd solution. And finally, the general solution now would just be x of t equals, so we've got them all on the board already. C1 times, the first solution was e to the 2t times -1, 0, 1. I'm actually writing this one all the way out. If you just wanted to write C1 times x1 plus C2 times x2 plus C3 times x3, that would be fine. But I just sometimes like to look at it so I can kind of get comfortable with how these things actually look on paper. The second solution is the longer one with the W's that we had to use. So we'll just add t times 5, 0, -5. I'm literally just copying stuff down at this point. The third term is C3 e to the t times the vector 0, 0, 1. And this then is the whole thing. That's the whole thing. Final answer. What do you guys think? Any questions there? Go ahead.
So the midterm, we don't have to do that there?
Right, on the midterm, if you just want to write C1 times X1, I do want to see this step written down. Again, it says you're supposed to solve it, you need to give me a general solution, but you could just do this as a shorter answer, and I would take it. Because you've already written down what X2 is, what X1 is, and what X3 is. So you could just lay that out here. Somebody in my first class was kind of observant, and they remembered that when I wrote down the mixed eigenvalue case, I had written it out like this, with the single eigenvalue as the first one, and then the repeated one being the second one and the third one. And they were a little bothered by the fact that in this solution, I took the single eigenvalue and made it into my third solution rather than my first one. Do you think that matters? I think it matters which one is x1, which one is x2, and which one is x3. It really doesn't. I mean, you're just adding it all up, right? At the end of the day, you're adding up a big general solution. So if this was your first term, and this was your second term, and this was your third term, and you looked at the person next to you and compared it with what's here, you would be like, oh yeah, that's the same thing. It's the same thing. So it doesn't actually matter. I generally like to do repeat lambdas first when I'm actually calculating things, because I want to know early on, is my matrix defective or not, right? For many reasons. Maybe I want to diagonalize the matrix, or maybe I want to know whether I'm going to need to use these W's. I can get that information sooner if I work on the repeat lambdas first. That's all. Okay. I think I will forego doing an example of the regular defective case. It's actually easier than either of these two. You will have one in the homework, and I'm sure that you'll find one in one of those sample tests somewhere. But it's the same process. It's the same process here. So this is it for kind of 9.5. Most of today really was just doing examples of it. The main thing is you need to learn how to build the x2 and the x3 if there's defective solutions, and this diagram will help you remember how to do the W's. And there's a lot to it. So if you don't get it absolutely perfectly right, try not to panic. If you've drawn this diagram, if you found the eigenvalues, if you do the null spaces, right? Maybe not every single thing is in exactly the right place. You can get a ton of partial credit, basically almost full credit, by just giving me the primary steps there. Guys, before we go, there's a question. Do I have any more time? I guess I'm talking like I've said. Am I done? I have 3 minutes. Oh, I don't want to be accused of taking anybody's tuition money for 3 minutes. So let me make sure that I take 3 minutes. And I want to just quickly talk about number 18 from the homework assignment. That was the one that got put up on the board first. We're going to do it real fast. I'm going to do some of your homework for you. So you can't complain about that, right? That's a good thing. So on number 18, this is from 9.4. They give you this matrix here: -1, -6, 3, and 5. And then they give you an x naught value of 2 and 2. And they just want you to solve this. Solve this system again. Okay? So really quickly, we have to find the eigenvalues. So let me just do my little 2x2 determinant to find the eigenvalues. And so I subtract lambda off of the main diagonal. I write down the formula for the 2x2 determinant. I'm going to get something like that. And let's just see if I multiply that out. If I multiply this out, I'm going to get a lambda squared, and then we get a plus a lambda and a minus 5 lambda, which is actually -4 lambda. And then I have -5 plus 18, which is actually 13. And that's my quadratic equation, which I have to set equal to 0. And this one does not factor nicely. I actually would need to use my quadratic formula for this. So the quadratic formula, -b, which is 4, plus or minus the square root of 16 minus 52, all over 2. And 4 divided by 2 is 2. And the square root of -36 is actually 6i, which is being cut in half. So it actually becomes 2 plus or minus 3i. Those are the lambdas. Those are the lambdas. Can somebody remind me, based on that, will my phase portrait, will it be a saddle, a source, a sink, an unstable spiral, a stable spiral, or a circle? 6 possibilities. It's an unstable spiral. And all you have to do is look at your lambdas. If they are complex numbers and you have a positive real part, you have an unstable spiral. Unstable spiral. Have I used up my 3 minutes? Probably.
Yep.
So here's the deal. Here's the deal, guys. For those of you who aren't done with this problem yet, you're gonna have to find the 2 solutions. The general solution will look like this. And to get it, you will have to use the Floyd technique when you have imaginary numbers. We've talked about that on Tuesday. So be sure to review the Floyd technique. But the last thing you have to do here, after you get this general solution, is you need to go back and plug in 0 for t, so that you can solve for these constants. So everywhere I see a t, guys, I'm gonna put in 0, and I have to set it equal to the value here, which is the initial value. Once you've done that, by the way, you're gonna have sines and cosines all over the place with this thing. But the good news is that the cosine of 0 is 1. Sine of 0 is 0. Nice numbers. This will not be difficult. You'll get nice values for C1 and C2. If you need more help with this, because I didn't have time to finish it, I will have office hours today and tomorrow, and I really encourage you to stop by. I'll be happy to help. That's it for today. Thank you so much for a wonderful class. I will look forward to the next time. Don't forget to do me an SOQ form before tomorrow. Thank you.